There we go. So welcome to the Data Tracks 11 o'clock with Guy Royce and Dungeons, Dragons, and Graph Databases. And Guy works for Redis Labs as a developer advocate, combining his decades of experience in writing software with a passion for sharing what he's learned. Guy goes out into developer communities and helps others build great software. Teaching and community have long been a focus for him. He's president of the Columbus JavaScript User Group, an organizer for the Columbus Machine Learners, and has even helped teach programming at a prison in Central Ohio. So if you haven't noticed, Guy's from Ohio. So that's one cool thing about doing this virtually is we've got a much broader pool of people to draw from. In his personal life, Guy is a hard-boiled geek, interested in role-playing games, science fiction, and technology, slightly less geeky interest in history and linguistics. In his spare time, he volunteers for his local Cub Scout pack, goes camping, and studies history and linguistics. Lives in Ohio with his wife, 3 teenage sons, and an entire wall of games. At some point, I'd like to talk to you about your wall of games, but not right now. So take it away, Guy. And tee up your screen, and I will share it with you as soon as you do.
There we go. Should see the screen. Hang on a second here. Teams likes to minimize when I share my screen, and it's like, no, I want to keep seeing Teams because I want to be able to see questions coming up in the chat on the side. So that's sort of a cue for everyone who's watching is if you have questions during the talk, feel free to throw them in the meeting chat if you can. I don't know if can they do that or not, Stan?
They can throw in the meeting chat or the Q&A. There's a Q&A on the side, but there's also the Discord chat we've been using. So either one of those. Okay. And I'll keep an eye on them.
I'm looking at the meeting chat for Teams, so if I see it there, okay, I'll respond to it. And if you see it in other places, Stan, just feel free to interject at an appropriate time. Yeah, feel free to ask questions. I answering questions. It makes the thing more interactive, and since we're virtual, this is the interactivity is harder to get because of the virtual environment, right? I don't see any faces at all except for mine and a screen full of slides. So yeah. Matt says he can't see my face. Matt, that's a blessing. You're fine. So welcome everyone. This is my talk at Dungeons, Dragons, and Graph Databases. I think all 3 of these things are cool. I guess both of these things because it's Dungeons and Dragons, right? And that's a cool thing. I hear actual dungeons aren't actually that great, and so I've been trying to avoid those. And dragons aren't real, so But Dungeons and Dragons is real, and it's good fun. So my name is Guy Royce. As introduced earlier, I'm a developer advocate at Redis Labs. Key things on the slide is you should follow me on Twitter. Actually, the most important thing on the slide for you as a viewer here is that I have a link to my GitHub, and all the code that I'm going to show you today, and these slides and everything are all up on GitHub, so you can get all that information there. So that's the link you really want to care about. And don't worry, there'll be a QR code later in the talk that'll take you there as well. So. I thought since this was a Dungeons and Dragons themed talk, I should probably present my character sheet. My name's still Guy Royce in D&D. I'm neutral good. I'm a dwarven bard, which is, I guess that means I play the drums from the deep. Level 5, got some armor class and hit points, but I really just don't get in fights, right? And then I got my ability scores here. Strength, I'm kind of average. Dex, I'm fat and old, so I'm kind of slow. But I'm a little tougher than I look. Not particularly smart or wise, but I'm very charismatic, which means that that I'm full of myself. So there you have it. But more importantly, as a D&D player, I've got a problem, and you may have this problem as a Dungeons and Dragons player as well. And that is you've got this dungeon, and it's full of rooms that need to be explored. And in those rooms, you have monsters, which are a source of experience points, which help you level up, right? And there are treasures guarded by those monsters, or sometimes not guarded by those monsters. And you want to go in there and try and increase your wealth so you can upgrade your equipment. You want to increase your experience so you can upgrade your capabilities. This is an important part of playing Dungeons and Dragons. But, how do we optimize this experience? How do we make this experience, how do we min-max this to hit every room, get the maximum gold with minimum danger, or how do we maximize our experience points, find the toughest monsters? And, in addition to being a Dungeons & Dragons player, I'm also a developer. And so I could build a database, right? I could build a relational database, and I could put all the rooms in it, and I could put all the treasures in it, and I could put all the monsters in it, and then I could query that database to figure out where I need to go. And that's one way we could do it. We could use a relational database. But another option would be to use a graph database. And a graph database is a completely different kind of database from a relational database. And we could, go through this graph, and we have nodes that represent rooms and treasures and monsters in this dungeon, and query it that way. So that's what we're going to do. We're going to try and model this dungeon using graphs, and we're going to try and model it using relational database, and we're going to see how they compare. So I've said graph database a few times, but what is a graph database? A lot of people haven't used graph databases, and they may have heard of graphs in general. But what's a graph database? Well, I can't really tell you what a graph database is until I tell you what a graph is. And a graph is, it's a mathematical term, right? So we've got this wonderful die 20 here. And a die 20 is is it a icosahedron, or yeah, it's an icosahedron. So I got one right here with me too. I have my chance icosahedron right here. Let's, oh crap, I got a natural one. But on there we have points, or vertices, the vertex. And those points, or vertices, are connected by edges. And so this is, a graph is a series of vertices connected by a bunch of edges. A die 20 is a graph, but not all graphs are necessarily, Platonic solids. They're not all die 20s. Sometimes they could be die 4s and die 8s. But they can also be a little more abstract than that. They can represent just nodes, vertices that have relationships. The simplest graph is the null graph. This is a graph that has absolutely nothing in it. There are no edges. There are no vertices. Nothing to see here. Move along. We can add some nodes to our graph, and now we actually have a graph. And it's still not a very interesting graph, because it's just a bunch of points floating in space. We've got nodes A through G here, and yeah, so we have nodes. So what, right? Well, what we can do with these nodes is we can create relationships between them, or edges. So these nodes, these vertices, they're interchangeable terms. Relationships, edges, interchangeable terms. But we can add relationships between these nodes. And now we have a little bit more of an interesting structure, because there's, A is connected to C and C is connected to A. And we can talk about this graph here. There's some terminology that we use to talk about it. We can refer to these nodes here, like node E is not connected to the rest of the graph. So node E is isolated. Actually, B and F are a small graph that are part of the larger graph, and they're isolated as well. Even though they're connected to each other, they're still not connected to everything. And even the big one in the middle is isolated as well, because it's not connected to the other. So if you've got this graph that's fragmented up into parts, those parts are considered to be isolated. And isolated is fine. Sometimes that makes sense for your graph. But we don't want to have an isolated graph for what we're going to do today. We're going to connect all the nodes together. And now that all the nodes have some path that leads to another node. So if I want to get from F to D, I can go from D to A to B to F. And this is now considered connected. You can also have a fully connected graph, which is where every node connects to every node. I mean, that's another thing. You see that a lot. The graphs that represent neural networks tend to work that way. One thing you notice about this graph, or may not have noticed yet, is that it's undirected. So A and B have a relationship, but there's no directionality. A doesn't connect to B, B doesn't connect to A, they just connect to each other mutually. And so a graph that doesn't have a direction to it is considered undirected. But we can put directions on these lines and make them arrows. And now it changes how the graph functions, right? So A is got a connection to B, A is related to B, but B isn't related to A, because that graph has a directionality. Or you could say it's related, but in a different fashion. But this makes the graph directed. We can also talk about the degrees of nodes in a graph. So the degrees are the number of edges that come into a particular node. So like on my 20-sided die here, this point right here has 1, 2, 3, 4, 5 edges, right? So it's got a degree of 5. So here node A has a degree of 3 because it's got 3 relationships. Node B, we can for a directed graph, we can talk about the out degree. That'd be the number of relationships that are pointing outward from this node. So B connects to F and C, so it's got an out degree of 2. And of course, we can do an in degree, which is its evil opposite. It's the chaotic neutral to the out degree is lawful good, or lawful neutral. So yeah, so these are ways that we can talk about graphs. They got degrees, they're connected, they can be fully connected, they can be isolated. You can have a null graph, all sorts of terminology here. One thing worth noting is there aren't any rules about these vertices. So there's not a rule that says just because A connects to B that B can't connect to A in a directed graph. You can totally do that. And there's not a rule that says you can't have A connecting to B 5 times. You can totally do that too. And you can even have a node connecting to itself. So there's not really a lot of rules on what can connect to what. A node can have a relationship to any node, including itself. And it can be either bidirectional, well, not bidirectional, but it can be, if it's directed, it can be going out and coming in from the same node with a relationship. And so this is kind of a 5-minute summary crash course in graph. So how does this translate to databases? Well, a graph database is simply a graph structure with a with data laid over top of it. So all of your nodes, instead of just being nodes that have letters, they can actually have a type that says what type of node they are. So here we've got rooms, we've got monsters, we've got treasure. These nodes now don't represent just a node on a graph, they represent rooms in a dungeon. They represent monsters in those rooms, they represent treasure in those rooms. And then we can add attributes to those nodes. And so like room 1 up here has got an ID of 1 and a name of the statue room. Every good dungeon starts with a statue room, right? And the monster has challenge rating and experience points. The treasure has a name and a gold piece value. And so we can attach data to these nodes. And then the relationships themselves can also have a type that expresses what their intent is. So the room contains a treasure. The room leads to another room. The room contains a monster. And so this is establishing these relationships with data. And you can actually put attributes on those relationships as well. I tend not to. Usually if I find myself wanting to put attributes on relationships, that means I have a noun. That means I probably have a node. And so I'll do that instead. But you can do that. And then this is just then very nicely represents a dungeon. So we have these rooms and they're, so room 1, the statue room, leads to the barracks, and there's a corridor connecting them. It goes both ways. Room 2 might have some sort of trap or slide that takes you into room 3, but you can't go back up. So it's sort of like a one-way road. And so we can represent this dungeon as a graph. It's kind of nifty, kind of cool. It is a database worthy of Mordor. Diving a little deeper into this, nodes, I tend to think of them, they represent items. Generally, they tend to be the nouns in your database. They can have labels and attributes like I just discussed, and they can be by themselves, just like in a graph. You can just have a graph full of room nodes that aren't connected to each other, and you could just query all those nodes. The relationships represent those connections, and they connect 2 and only 2 nodes. They have a type, which is very analogous to the label that you have in a node, and they have directionality. In graph databases, they typically have directionality, and they can have attributes, which I also mentioned. An important thing about nodes, about relationships between nodes, is if you delete the node, the relationship goes away. Nodes can exist without relationships, but relationships can't exist without nodes, which kind of makes sense, right? I mean, if you look at your D20 here and you get rid of this point in the end, then it just collapses all those facets. There's no relationships there anymore to maintain. And so those are the key things that you deal with when you're dealing with a graph database. I think they kind of read like sentences. where you got sort of a subject-verb-object relationship here, where you've got the room contains a monster, and that directionality sort of shows the subject-verb-object relationship. And I think personally, I mean, there's the direction is arbitrary. You could have an arrow pointing to the left that says a monster is contained by a room, and that is grammatically and graphically correct, but it's also basically putting it in the passive voice. And as my English teacher told me, the passive voice is to be avoided. So yeah, there you have that. But I find that if my graph representations read like nice nifty sentences, I feel like I'm doing it right. I'm creating a nice semantic structure. So that's a lot of theory. Let's get into some of the more some actual like crunchy programmer things, right? Let's see what this thing actually looks like in reality. So because we've still got a problem, right? And we've got all this theory, but we still got the problem, which is we've got a dungeon and it's full of rooms and it's full of monsters and it's full of treasure, and we need to find the best ways to go through it. So how are we going to solve it? Are we going to solve it using a relational database? Or are we going to solve it using a graph database? Well, I'm going to go through and I'm going to compare and contrast these two. I'm going to show the SQL statements we use and the query language we would use for graph databases, for a few popular graph databases. So if we're going to do SQL, if we're going to use a relational database, of course, we're going to use SQL queries. And so, well, we all know what SQL queries are, right? Select our room.id, the name, the treasure ID, the name, and its value, and the monster ID and its name, its challenge rating is XP. You select all the fields from all the rooms, or from all of the entities, and then do a join, right? This would return everything that's in the database, assuming that we don't have any left joins or anything like that. We didn't set this up as left joins. And so this is how we interact with relational databases. So how do we interact with graph databases? Well, we've got a query language for graph as well. It's called Cypher. It was created by the folks at Neo4j, but it's been released as an open standard. I work for Redis Labs, and so all my stuff's going to be on Redis Graph, but we use that same language. But here, the Cypher query language, you do matching. You've got these matchers where you find a particular pattern in the graph, and it matches those, and then you can return properties from everything that's matched. So here we match a treasure that is contained by a room, and a room that also contains a monster, and then we return those 3 nodes. And then we'll get all the attributes on those nodes as well. The matching is actually the really cool feature. It's the key concept, I think, to understanding Cypher queries, because you're specifying a pattern that, well, matches a structure in there, and it will return everything that matches it. And it's cool because it kind of looks like a graph, right? On here, the left, the r::room matches a room node, and it's got parentheses, which makes it look kind of round, which is how we represent nodes when we're drawing graphs on like a whiteboard or something. So r::room matches any node with the label room, and assigns it to the variable r. m::monster matches any monster node, and assigns it the variable m in the same way. And then we have a relationship here. So we've got our nodes with our little rounded bits, and this relationship is drawn like a little arrow, ASCII art arrow, showing the directionality of that relationship. We want rooms that contain monsters, and we can again look for ones that have the label or the type of contains, and we can assign that label or that relationship to the variable c. And so this will go through the graph and match every single instance where a room contains a monster, and then once you've matched those, you can do all kinds of things with them. So let's look at creating rooms. We want to add some rooms to our database so we can start querying the dungeon. And so we're going to look at how we do that with SQL, which is a simple insert statement. We just call insert into rooms, pass in the columns we care about, pass in the values as the values, and boom, it inserts a record into a database table for us. In graph, we don't actually need the table. There are no tables. It's schemaless. So we create a room. We just create a node of type with a label of room, and then we assign it to the variable r, and then we set properties on that variable. So r.id is 1, r.name is statue room, and these can be anything. There's no schema here, so we could say, r. Is trapped equals true. r dot has really cool murals. We could have an r dot description, which would give you a more verbose description, right? We can put whatever we want in there. We're just going to stick with the name of the room for now and the ID. But this allows us to create using Cypher. If we want to then go and query the rooms that we want to just create, so we've created, we're going to read. I bet you we're going to do an update. Well, I just flipped everyone off, didn't I? An update and a delete. So we got create, read, and we're going to do update and delete. So here's the reading. This is the classic select statement. Select star from rooms where ID equals whatever. In graph, we will do a match. And so here's that match, right? That we showed earlier. Match the pattern, anything that's a room, assign it to R, and then we can put a where clause on there saying where R dot whatever property we want is equal to whatever value we want. Here we're looking for a room with an ID of 1, and then we return the room. So this is actually in some ways kind of similar. The matching's a little more sophisticated. And you'll see how it gets more complicated as we move through this. For updating rooms, we do a basic update statement. We decided we don't want the statue room, we want the statue hall, so we're going to rename it statue hall. In graph, we match the room that we match all the rooms, say, and reduce that down to just the room where the ID is 1, and then we use that set command again, just like we did on creating. So we match a room with that type or that label of R, or of room, assign it to R, filter them out to get just a room with an ID of 1, start setting properties on it. And so this would be a way of updating it. It would also be a way of adding additional properties because, again, there's no schema here. And to delete a room, delete from rooms where ID equals 1. Perhaps one of the scariest statements to enter in a SQL database. In graph, we match that room like we did before with the same where clause. You see in a pattern here, right? We match where. And then now that we have a variable, we can just delete it. And so we could actually do match R colon room, delete R without the where clause. So that would delete all rooms from the graph, which is kind of akin to saying delete from rooms without a where clause. Just delete everything. Again, kind of a risky statement. Deletions are always kind of risky. But yeah, so these are the basic CRUD operations in SQL and graph, and you can see they're different. A relation database is schema driven, and graph doesn't have any schema, but so far they really aren't that terribly different. I do want to make a note on my nodes on the syntax. So I'm using the syntax where I say where r.id equals 1 on the match. So I'll say match a thing where condition. But you can also embed that inside of the node using curly braces, and then do basically a JavaScript object sort of syntax or a JSON sort of syntax, where you can say ID is 1, comma, name equals colon is another thing. And that's another way of matching without using a where clause. So there's more than one way to do this. And that works for create as well. You can create a room and just give it properties. And so lots of times when you're creating, this is a convenient shortcut. So it's another option. So, and then of course, if we want to create monsters or if we want to create treasure, it's exactly the same pattern, right? Just different tables, but it's the same pattern. So far, we've created a relational database and a graph database. Our relational database has got a table called rooms with an ID and a name, and we got 3 rows in there. We got 2 monsters with some data about them. We have a couple treasure items with some data about them, and they're all just kind of hanging out in their own tables. There's no relationships between them yet. And it's the same for our graph database. We've just plopped a bunch of nodes in a graph. They're hanging out there, but they're all isolated. It's completely disconnected. There's no connectivity in this graph at all. Everything's got a degree of 0. So what we want to do is we need to start putting some things in the rooms. So let's put a monster in the room. And let's do that with graph first. So we're going to put a monster in the room using a graph database, or with a relational database, I'm sorry. And so to do that, what's the first thing we have to do, right? Well, we need to alter the monsters table. The monsters table doesn't have any way of relating to the rooms table because we didn't add a column for it. And in a relational database, you create a foreign key. So we alter the table, and then we update the monsters table to reflect that new relationship. So we had to alter our database schema in order to do this. Not super crazy, but altering the schema is something you'd probably really rather do up front rather than after it's in production. Because then you have to update, you have to populate that newly emptied field. In Graph, to put a monster in a room, you just match the room. Say, give me room ID 1, and you match the monster, and you create these variables R and M, R for the room, M for the monster, and then you can create a relationship. Say now that I've matched R for the room that I want the monster to be in, and I've matched the monster I want to put there, just create the relationship between them with the contains. So the room contains a monster, and so this you got the nodes. You see the roundness of those nodes, and you got the little arrow, and it's got a label on it and everything. And so this is how we put a monster in a room. Pretty straightforward. You might be tempted when you start with Graph, and I was when I first started looking at this, to create a room with your properties on it to match the room that is out there already. So I know I have a room with an ID of 1, so just match this for me, please. And then match the monster, and then just put the contains right between them. This seems like, well, it'll just match the things that exist and then create the relationship, right? No, it doesn't do that at all. What will happen instead is these will create duplicate rooms and monsters, or new ones with the same ID. And then we'll create a relationship between the newly created things. So you need to match them in the match statement. That's sort of a querying operation. Is the create statement will create whatever you tell it to create. So be careful with that. To put treasure in a room, it's the same pattern. Here we have to alter the treasure table. We have to create relationships between the rooms and the treasures. And a Graph, again, putting a treasure in a room is just a matter of matching the room, matching the treasure, and then using create to create that relationship between them. Same pattern. And so now we have a better relational database, right? We have the rooms, and they have a one-to-many relationship between it and treasures and it and the monsters. So a room can have multiple monsters, a room can have multiple treasures. Our Graph database now is not as isolated as it was before. The rooms all have some degrees to them, right? The statue room contains Alice the elf, and the barracks contain a +1 sword. I want to go to the barracks, and the armory has got a pile of coins and Bob the ogre. But I still just have a list of rooms, and now I have a list of rooms, what's in them. And so we're still at a position where the Graph's got a couple features that are nice. Its lack of schema makes it, and its lack of needing foreign keys makes it a little more flexible. But they're not really doing anything fundamentally different. So, but let's get into the part where there actually is some difference. And well, actually, before we do that, let's go be a munchkin with the data we have, and then we'll get into some of the things where graph excels and relational databases are hard. So it's munchkin time. We're going to try and min-max optimize our dungeon crawl experience. We're going to try and hit the rooms that have the most monsters, perhaps because we want to maximize our XP, or we're going to hit the rooms with the most treasure because we want to maximize our treasure. So let's farm all the XP that we can out of this dungeon. And to do that, we need to do a join. So we can select all the rooms and their properties. From the rooms and the monsters, select rooms, the ID, the ID and the name of the room so we know where to look, and the monster's XP, so we know how much XP is in that room, from those two, the room and the monster, where the ID matches the room ID, right? So this is using that foreign key to create a join. So let's do a join on these two tables and order it descending by the experience points. So that means the greater experience will float to the top, the smaller experience rooms will float to the bottom. If there is not a monster in the room, this join will not return that room, and we wouldn't care because we're trying to find the greatest XP, right? To farm all the XP in Graph using Cypher, we could match all the rooms that contain monsters. So we got a match here that's a little more sophisticated, right? We're not just matching on a node, we're matching on a node with a relationship and to another node. And that will match every room that contains a monster, and it'll match you'll get the room assigned to R, the monsters will be assigned to M, and you can even assign the variable contains to a variable. The relationship can be assigned to a variable as well. But we don't care about that. We just care that it's there. And then we can return those same properties just like we did in SQL and order them in the same way that we did with the SQL. But now we can farm all the XP from a graph. And it's the same for getting the gold. When you maximize your gold, you can, very similar select statement, very similar join, very similar order by, with the descending so that the high gold piece rooms float to the top. And the graph query is going to look very similar, except instead of monsters, now we're looking for treasure. So these are comparable operations. So so far so good. So what, right? Right now, I haven't really done anything with a graph database that I can't do with a relational database. Well, we're going to change that. We can see where graph starts to make a lot of sense. And that's when it's time to relate rooms to rooms. We want rooms to be connected to rooms. And we want to do this so we can figure out the best paths through the dungeon. So if we want to have a room that connects to a room, how do we do that in a relational database, and how do we do that in graph? Well, in a relational database, we need to create a new table. And that table is going to map connections, room to other rooms. So we've got 2 foreign keys, and that's all that's in this mapping table. Its purpose in life is to take a one table and create a relationship to another table, but we don't care about the table ourselves. Our app doesn't care about the table, but we need to have that there to create that many-to-many relationship. In this case, we're doing a many-to-many back to the same table. We could do a many-to-many for a separate table as well, of course. But we create that table, and then we insert into that connection table the foreign keys. And you'll notice that we have to do it, both directions here. And actually, if you look here, you'll see a 1 and 1. There's the room connecting back to itself. 1 connects to 2, 2 connects to 1. So we have to do both entries here, and that's fine. We have to do that in graph too. But this is how you would create this structure in a relational database. Querying it is where it gets challenging. To connect rooms in a graph database is actually no different than connecting rooms to treasures or connecting rooms to monsters. It's just a different relationship. So here we're going to match the room ID 1, room ID 2, and then we just create that relationship between them. Room 1 leads to room 2. And so it's exactly the same query. We didn't have to alter any tables or any schema. We didn't have to create any new tables. We just created a relationship because we wanted one there. And so that gives us a relational database here, which has gotten a lot more complicated. We can barely see the dungeon under the relational database. It's very obscured. And we've got our 3 entities we care about, right? We got our rooms, we have our monsters, and we have our treasure. But then we have this other table over here that's just there because we need it to relate things to each other. Our graph now actually looks complete. It has literally been placed on top of this dungeon to show the relationships between the rooms. It's a little easier to wrap our head around. It's a very intuitive sort of structure here. But this is what our graph looks like so far. We've got a bunch of rooms and monsters and treasure, and all the rooms are connected to each other in different ways. And life is good. So now it's not Munchkin time, it's Super Munchkin time. I'm going to go into some of the queries that we can do with graph that I'm actually really not sure how I would solve these in SQL. And that is we want to find paths through the dungeon. What's the path to the, from where the room I'm in right now, how do I find the room with the most gold? What's the shortest path there? Or, where do I, what's the path out of the dungeon? Or what rooms are around me? Those are easy questions to ask the graph database. They're more challenging with SQL because you have to do joins back on itself against that same rooms table. So here we have this idea of a variable length relationship. And so we've got our basic match that we've been looking at all along. Room leads to a room, but we've added this little asterisk here. An asterisk just means many. It means go through as many nodes as you need to find the second room. Match them all. So room 1 that leads to room 2 could leads to room 1, or room 1 leads to room 5, which leads to room 6, which leads to room 7, which leads to room 2. That would match this. And so it lets you match, if these are next to each other, they'll match it, but if there's a longer path, it'll match those as well. And so it stretches those out. It will match any length of a relationship as you want. So you can find these long paths through the graph. And you can limit it. You can say, well, no, I want only things that are within 1 to 3 hops away. So a maximum of 3 relationships here, which would be 4 nodes. So you can cap it. You can give it a minimum. I could say 2 to 5. I put any numbers I want in here, right? They're numbers, right? And then this is the maximum number of hops. And so this is a way of restraining it. Saying, no, show me all the rooms that are within 3 hops of me. Right? We could do that. In fact, that's our next query, right? What are the nearby rooms? I'm in room 1. I want to find all the rooms that are within 3 hops of me. So this query will do that. Match the room with an ID of 1 with a leads to relationship that's at least 1, but no more than 3, and leads to another room. Yeah. How would we do that in an SQL database? You'd have to join back 3 times on your SQL query. And then just return the IDs of the names of the rooms. This will give us all the rooms that are nearby. What about the nearby rooms with the most gold? That sounds promising, doesn't it? I'm here. Where do I go next to get the most gold? It's like following breadcrumbs, right? Little golden breadcrumbs. Well, we can match a room that leads to up to 3 rooms away, another room that contains a treasure. So here we've got our room. Here we've got our leads to with a maximum hop of 3. Another room, and that room that it leads to must contain a treasure. If it doesn't contain a treasure, I don't want to see it. So, and then we can return the room, the name, and the gold piece value in the room, the gold piece value of the treasure in the room, and order it descending by the gold pieces. And now we get a list of rooms that are nearby in, shall we say, priority order. And then we could also, sorry, I forgot to mention here, there's that limit 1. And so that would give us the room within 3 hops that has the most gold. But if we just wanted to see a priority list, we could do that as well. We could find, maybe we're a completionist. Maybe that's the way we like to play D&D. And so we want to maximize our, we want to hit every room in the dungeon. What's the longest path? What's the shortest path that hits every room? Which is another way of saying the longest path. So I want to go from room to room. So assuming I can start at any room, give leads to star, multiple hops, any room. And you'll notice here we're doing this P equals. And so what we're doing here is we're taking the results of this match and we're assigning the pathing information to P. And then we can query P using some functions. And so instead of returning like the rooms, we can say, how many nodes are in P? That'd be how many rooms, right? And we can get all the nodes. We can call nodes P, get all the nodes. And we can also say, how long is P? How many nodes are there? And we can even rename that as length. And then we can order it by the length and limit it to 1. And this will give us the longest path of all the paths that were matched. This match here will match all rooms, all paths without recurring. So, this could be an infinite loop, right? Go back and forth multiple times. It catches that, don't worry. But this finds the longest non-recurring path, I guess you could say, which is not to say that it won't go back on itself, but it'll hit everything. It just won't loop, is what I'm trying to say. And then we can limit that by 1, and we find the longest path through the dungeon. And now I know, now I have a map. I have that I can follow to optimize my route through the dungeon, to make sure I hit every single room. And we could even find the room with the biggest treasure, which is probably what we all want to do more than anything, right? Here we can we use the with clause in our Cypher query, where we match anything that's a treasure, any node in the graph that's a treasure, assign it to the variable max, and then we can take the max of max.gp, the gold piece of the room with the most the room's treasure, and then whatever the max value is, we'll assign that to the max GP variable that we're going to use later. So this allows us to match things and pull values out of them to be used in later matches. And so here we've got a room, and it contains treasure. So this is the basic, find all the rooms with treasure, and then match them where the gold piece value is equal to the max gold piece value that we computed in this previous match up here. Now, this does mean if you have two rooms that are tied, they'll both come back. I think for our purposes, that's acceptable. And then we just return the name of the room, the name of the treasure, and the gold piece value. Now we know where we want to go. And we can combine all this stuff to create more complex queries, right? We can find the path to the room with the most amount of gold. And so we've taken this query that we just saw here, where we're getting the max treasure value, and then we're getting the room that has that max treasure value, and then we're assigning that to a destination. And then here we match the path from our start room, which leads to the stop room. So this is from any room, leads to the room we want to go to. Oh, no, sorry. No, this matches any room to any room with as many paths as we want. And we say we want the start room to be 1. We're going to start at the beginning of the dungeon, and we're going to stop at the destination. And then we can, again, get the nodes and the length like we did before. And now we've got all the paths from the beginning of the dungeon to that room that has the most gold. And we can order it by the length and limit it to 1. That will return us the shortest path. So kind of a cool query. Do you want to see if this is real or not, or guys just making stuff up? I've got a demo ready. So let's take a look at the demo here. I've got some JavaScript code that generates a random dungeon. I'm using Lodash here and some randomizer. I got a whole bunch of stuff in here, and all this code's out on GitHub. But it just generates a random dungeon name. So like the dungeon here has add rooms, add entrances, connect rooms. Lots of code in here. It's all Node. You can go check it out. I've got a little name generator that I'm using, a fantasy name generator. Got a randomizer to roll dice for me. So like give me a random artifact type, so I can generate random names for all these things. Get our rooms, our treasure, a bunch of fun stuff out here. It's pretty easy to get it up and running. The main thing is you need Redis graph up and running. And if we look at the Redis executor here, it looks at an environment variable or a local host. I've got mine pointed to Redis Enterprise Cloud because their graph can be a little compute intensive, and I have a very underpowered MacBook. So I'm going to use a remote one out in the cloud instead. And so I've got my host, port, and password in environment variables, which I'm not going to show you. But to run this, it's just a matter of doing npm start. It'll kick off server.js, and it will create us a random dungeon. And it does it without much fanfare. But we can go ahead and, using the Redis CLI, access this. Actually, I can't do that from the Redis CLI because I'm not connected to the right one, but we can do it with Redis Insight. Redis Insight's sort of a GUI client for Redis. I've got it set up already to talk to my cloud instance. So let's go in here. Let's do sort of the select star, the select world, the select star from table sort of query for graph. That is match n for node. This will match all nodes in the graph. Return n. If I enter, and the cool thing here is that it actually shows all the nodes in this cool structure. And if we zoom in, see, it'll start providing some data here pretty soon. Yeah, there's the vile chasm, the dusty chamber. We got 5 Zorns. That sounds fun. 3 goblins, -1 cursed sling. Random treasure is great. And so this is all the nodes in the graph. And the cool thing with, you know, we could do something a little more specific, like let's return all the rooms. Right, so now we're matching R: room, return R. And this will give us all the rooms, and you'll see it brings in its relationships automatically. We'll zoom in here. And there are, let's look at the dank warren. We can drag that over there. If we click on it, it'll show us it connects to filthy barracks. I clicked on filthy barracks. The dank warren here, it pulled up the gorgons. So the dank warren has 2 gorgons in it. Let's go ahead and, my example has a dungeon in it as well, because I wanted, you know, sort of a container for everything. So let's match D dungeon, return D. And we're going to get 1 node back. But my dungeons have names. It's the gloomy caverns of Urzazil. Yeah, Urzazil. The gloomy caverns of Urzazil. And if we double click on this in Redis Insight, we'll see that it has the dungeon has an exit, it has an entrance, has an exit, has an exit. So dungeons have entrances and exits. And if we click on the narrow room, we see that it's got quite a few monsters and no treasure. Right, so we can sort of explore our graph here. Not finding the treasure that I want. If only there were a way I could query this and just find the treasure. Oh wait, there is. Let's match our room that contains a T treasure. And we return R and T. There we go. That's more like it. As we zoom in here. So the big pit has a pile of coins and gems. The filthy barracks has elven plate, -1 cursed sling, and a +3 glaive. It's got the dagger of Gragluar, cursed great axe, all kinds of great stuff in this dungeon, right? And if we want to see how much that dagger is worth, we'll click on it here, and we'll see down here it's got the name and it's worth 500 gold pieces. So let's do some of the more sophisticated queries, and I'm not going to try and do these from memory, because quite honestly, we matched rooms and treasures there already. Let's match the longest path in the dungeon. I've got a query for that already. So match P equals dungeon has entrance room, leads to rooms, as many rooms with as many hops as possible, has an exit to the dungeon. So find me a path through the dungeon, and return the nodes and the relationships and the length, and there's our order bys and stuff. And this is a little bit slower of a query. But if we look at this from a table view, which all these have a table view, right? I can go in here and see, you know, all the things that I queried. Like here's all the rooms, right? This lends itself better to a table view. So let's look at the table view, and we'll see that we got there's nodes P has 17 items, has 16 relationships, and the length is 16. If we expand the nodes, we can see all the nodes that we need to go through. I saw musty pit and I thought it said mosh pit there for a moment. Like I didn't think I put a mosh pit in the test data. And so it's, you know, we got all of our properties on that node. It's the gloomy cavern. Here is the properties on the first room, which is the narrow room. It's got an ID of 16. So we can query that stuff fairly easily. And let's see, let's do this last one here. Shortest path to the most gold. That's actually a nice short path, isn't it? Length of 2, 3 items in the nodes. So go from the damp jail to the vile chasm, and then to the painted warren. All your warrens should be painted, shouldn't they? So here we found the shortest path to the most gold. So this stuff works. It's fairly performant. If you think about what's happening here, how much graph there is to walk, it's excuse me, surprisingly performant. So I got about 5 minutes left here. So I've given you a really impractical application for this, gaming. But what are some real things we can do with this? Well, you could actually use this as a database for games, right? I mean, that's one. It's not one of my choices I have here on my little slide, but it's a totally viable option is to use it as a background, as a data store for games. And Graph could be great at that. But it's also, there's many things that are naturally graphs. Maps are naturally graphs. Social networks, friends of friends and that kind of stuff. Querying those to find possible future friends on Facebook, for example. Graph's great for that. Genealogy is really just another version of that problem, right? It's who's related to whom. If I was building some sort of genealogical database, Graph would be a really reasonable choice. You could use the variable number of hops to say find all the great-grandchildren of this person, right? Transportation networks, a map lends itself naturally. The roads are the edges and the intersections are the nodes, or vice versa. And if you use mass transit and you have bus stops and train stations, it could all map into there very nicely. And I think logistics is a cool one. You could actually create a graph of your logistical network that shows someone got some poisoned spinach. It's got some E. coli on it, and they were at this store. What are all the farms that this store sold goods? Where are they from? If you got a graph showing your logistics network, you could make those sorts of queries. Here's some resources. Of course, I'm using Redis graph. It's not the only choice in here, but I work for Redis, and so it's the one I like. But you can go out and get Redis at redis.io and Redis graph at redisgraph.io. Get that up and running. There's also a great Docker image, which is what I usually use because that's just easier. The Cypher query language, I mentioned it was created by Neo4j. Neo4j has, of course, a graph database as well, and they created this Cypher query language. They've been in the market longer, and so their product is a little more established. It's more established is the wrong word. It's more full-featured than Redis graph is today. Although Redis graph being in memory is a lot faster, especially for larger queries. And we've taken advantage of some fun linear algebra tricks to make that happen. Open Cypher is the Cypher query language that they've opened up to the public, which is why we're able to use it. And of course, if you want to get started with Redis graph and Redis, I've got a blog post up on redislabs.com that's kind of gives a similar example to what I'm doing here, and it has links to a lot of these resources. Check us out online. We got a Discord server. Go to GM Kachu. I love that it sounds like your dungeon master sneezing. We got community forums. We got Redis Enterprise Cloud is where I ran all my graph stuff today. And I heard a question.
So we have a couple questions.
Okay. Here's all my slides. Go get those real quick. And
if you want to pop that into Discord, then that'll be there.
Yeah, I will afterwards.
Cool. So let me read through them, and then you can answer them at will. Which model would I be better thinking data in terms of undirected or directed relationships?
I've only really used it with directed relationships. That's what Redis graph does itself. I haven't played around with the other graph databases enough to know I don't think there are any graph databases that create non-directed relationships. I could be wrong on that though. I mean, the Cypher query language can certainly support it because it's got, it's got the little arrows on it, right? And there are ways you can do like bidirectional queries. It's like, I want a room that has treasure in it or a treasure that has a room in it. And I don't care what the directionality of that relationship is. So you can query it that way. I've been using directed graphs for all of mine. Okay. And I think that tends to lead to more intuitive data structures.
Great. We have a couple more. How expensive is it, the update and delete in GraphDB?
I don't know that I have good benchmarking numbers. I found in practice for the demos that I've been putting together that it just happens. You're grabbing a node by its ID, you're updating it. Graph is, when you scale graph up, it does get slower than relational databases. And so that should be, that's a consideration when you're choosing graph for your problem. because graphs are represented in memory as matrices, and all the relationships are points in that matrix, and so you have all the relationships, all the nodes on the top, all the nodes on the side, and then is there a relationship between them is the intersection, and so it's the square of how many nodes you have. Now you can resolve that by using sparse matrices, which is what Redis Graph does, but that's still slower than some optimized SQL queries. If you had a bunch of, and it's slower than a lot of just optimized Redis queries as well. And so Graph is a tool that I don't think I'd want to deal with a graph that had 1 billion entries in it. I just don't think that would work. So I think that answers the question.
Yep. In the graph database, you created a relationship from room 1 leads to room 2. Do you also have to make a relationship 2 leads to 1?
Yes, you do. So since it's directed, in effect, if you say room 1 leads to room 2, you're creating a one-way corridor. And if you want to be able to go back the other direction, you need one creating the other direction. And actually, if you look at my queries here, you'll see that. Let me go to the graphic view here. I know I'm running really tight on time here.
That's okay.
Like,
you're running up
room 8
lunch,
and
so
room 10.
Fine.
You can see there's 2 relationships there, right? So I did, in fact, create, like, the big jail connects to the musty pit, and the musty pit connects to or leads to the big jail. So, but then, like, the contains relationship here, it wouldn't make sense to have treasure contain a room, right? And so that just needs to be, unidirectional.
What is the best way to integrate a GraphDB with a web service, REST or GraphQL, or something else, gRPC?
So that's a different kind of. So like a graph database, the graph database is a backend solution, right? And so you could put any kind of layer of abstraction in front of that one. You could put you could put a bunch of REST services that just hide those queries behind it. You could use GraphQL to do that as well, and you could use some sort of RPC mechanism, and so it's sort of orthogonal to that. So
great. Well, we have a couple more minutes. Like I said, you're running up to lunch, so
okay.
You're welcome to take a couple more minutes if you wanted to say any last things.
Yeah. Okay. Well, here's the link to the slides. Feel free to hit that QR code. I swear it doesn't go to a Rickrolled YouTube video. One of these days, I'm actually going to make it go to a Rickrolled YouTube video. It's going to be great.
Or Nickelback.
Is that the new Rickrolling in Nickelback?
Yeah.
And that